Okay, welcome everyone to today's theory lunch. So we have Sam Hopkins. Sam did his PhD at Cornell with David Stoider. Now he's at Berkeley. He's a Miller Fellow, postdoc at Berkeley. And he's gonna, well, Sam has like amazing set of works, but today he's gonna tell us about some very recent amazing work on how to do some computation of mean and covariances. Yeah.
One sec. It's the only references I'm going to write in the whole talk, but I just want to be honest. Oh, we'll just abbreviate that one. Okay. Hi, I'm Sam. I'm from Berkeley. Thank you all for coming. This talk is going to be about how to compute medians in high dimensions. And it's loosely based on three papers, one by me that's in the Annals of Stat earlier this year, one by Yeshwanth Cherupanamjeri, Nick Flammarion, and Peter Bartlett, where I'm going to steal most of the actual math because they did a much better job than I did, and one by Yeshwanth, me, Tarun Kothariya, Prasad Raghavendra, and Nilesh Tripurananani, which is in submission. Okay. So, what's up with the median? Let's remind ourselves what a median is in one dimension, right? What's the median? If I have a set of points on the line, then the median is, the point in the middle, right? Like this guy, median. So, why do you use the median? There are lots of reasons you might use it, but it's basically a way to summarize a data set by a single point, in this one-dimensional case, literally a number, which is not as badly skewed by outliers as the other natural thing you would do, which is the mean of the data, right? So the median is ubiquitous in statistical situations where you have a data set where you think that outliers are having a large effect on the mean, and you want some other kind of summary of your data. So medians are super familiar in one dimension, but these days we care about high dimensional data, right? We care about lists of points not on R, but in RD for some large dimension D. And the problem that there exist situations with outliers that are skewing the mean doesn't go away in high dimensions. And so we would like generalizations of the median to high dimensions. So this talk, at least the first half of it, is going to have two questions. Medians in high dimensions, in RD. Question one will be, how do you even define medians in RD? And question two, how do you compute them? Okay. So in order to measure our success at constructing a high dimensional median, we need a metric, right? We need some kind of goal. We need some way to capture this intuition that the median is robust to outliers in a way that the mean is not. And of course, there are lots of different ways to formalize this, and different ways to formalize it might lead to different notions of high dimensional median. But here's the one that I'm going to choose for this talk. I think it's reasonably natural. So let me state a fact, which in some sense captures the robustness of the one-dimensional median to outliers. Okay, so here's a fact. Suppose that you have a random variable, and suppose that it's just real valued, and suppose that its variance is at most 1. Okay? So I'm not going to make any assumption even about its third moment. It could be infinite. Then if you take n independent copies of this random variable, and you take their median, and you ask how far is it from the mean, the true mean of the random variable, what you will find, you could ask this for different kinds of probabilities or whatever, but it turns out that this has distance order of 1, like a constant number of standard deviations, with extremely high probability. 1 minus 2 to the minus number of samples, right? So with all but a very tiny failure probability, many constants will be murdered in this talk, and probably there's a constant sitting here. But with all but very tiny probability, the median of n samples is a constant number of standard deviations away from the true mean. Okay? And for comparison, let's ask what happens with the mean, right? Comparison to the mean, the average of samples. Well, a couple things happen. One is that actually this is much closer to the true mean, like 1 over root n distance, with probability 0.99. But that's pretty different, right? With probability 1 minus 2 to the minus n, if all I have control on is variance of this random variable, I expect that this list of samples could be kind of crazy, right? All kinds of strange tail events are going to show up. And the point is that the median is robust to those tail events, whereas the mean is not. How do you see the mean is not? Suppose I want to bound for the mean that gets this super high probability. All I could do is I could use like Chebyshev's inequality or something, and the quantity I get on the right-hand side would be like exponential. It would be way, way worse. It would not be order 1. Okay?
Are you assuming these random variables are independent?
Yes. Yes. I'm always going to talk about independent samples from this random variable. Good. So my goal is going to be to get a high-dimensional median which captures this notion of robustness. Okay? So my goal is to find some definition of median of a set of vectors x1 up to xn. Now they live in Rd, such that if I have a random vector with covariance at most identity, that's like saying in every direction the variance is at most 1. I would like to have that the distance, now measured in L2, between the median and the average, the population average, is, let's say, less than order 1 with probability 1 minus 2 to the minus n. Right? This would be the high-dimensional analog. It's not even clear this is possible, but that's what I'd like to do. So now we can say there are actually lots of candidate definitions of a median in high dimensions, right? This has been studied for forever. What's one natural thing? We'll just like take the median in every coordinate or something like that, right? Or you can do this something fancier. You can do something called geometric median, for which there's famously a nearly linear time algorithm. But the problem is that these things don't actually achieve this goal. And up until a couple of years ago, we didn't know a definition of high-dimensional median which did better than some dimension-dependent number here, like square root of d, is what it turns out you'll get for saying, oh, shoot, I'm really sorry.
That's fine.
Well, useless. Some dimension-dependent number like root d. So, should I get this on the right way, or am I supposed to have it like the other way? It doesn't matter. Okay. Okay, cool. But it turns out that if you could do this, there's kind of a killer application, which I'm not going to go into detail on because I really want to focus on medians. But the killer application is to estimating the mean of a heavy-tailed probability distribution. Okay, with very high probability success rate. So it turns out that if you can do something like this, what you can do is find an estimator for the mean of a random vector whose confidence intervals, whose like success probabilities are as small as they would be if that vector were Gaussian, and I use the empirical mean. So like if it were a very well concentrated vector, but assuming only that that vector has bounded covariance. Okay, so you can sort of pretend that whatever random vector you're estimating is Gaussian, even though you basically have no control on it. Okay, so that would be the killer application of a median like this. So now, let me tell you the right definition of the median that will get you something like this. And this comes from a paper by Lugosi and Mendelssohn from 2018, early 2018. So, definition. Let's say that a point in Rd with respect to some list of points x1 up to xn is R, P central if So here think of r as a number bigger than 0, and p is like a little number. It's like a percentile, 0.01. If for every unit vector u, or unit vector v, let's say, if I look at, here's r, here's actually the direction v. Okay, so let's suppose I take all my data, I take my x1 to xn, I project them onto this line. So here's like x1, here's x5, and so forth, x3. And now I look at where x is. And what I want is that x captures all but a p fraction of the samples, of the points. If I look at an interval of radius, say 2r around it. Okay? 2r. And what I want is that outside of that should be at most p times n points x. Okay? So formally, you're saying that for every direction v, the number of xi's such that xi, if I project in direction v and then look at the distance to little x, that this is bigger than r, this is less than pn. Okay? So this is saying please be close to the middle in any direction. Yeah?
Is there an absolute value around the interval?
In my definition, you're saying?
Yeah.
There can be. You can always look at v and also minus v, and you lose a factor of 2 here. So it doesn't matter that much. But yeah, you can have an absolute value if you feel like it. So think of p as being like 0.01. We're saying please capture the bulk of the data in any direction. Okay. So if you want to get some idea for what the set of rp central points looks like, let's think about what it is. Well, I sort of have, they have to satisfy some property for every unit direction. And what is the property they have to satisfy? Well, they have to lie in some interval, right? So I go to the 99th percentile over here, and then I fatten it by some distance r, and I go to the 99th percentile here, and I fatten it by some distance r. And if you think about what that looks like in high dimensions, it's a big intersection of slabs. Okay, so here's one for the direction v, which is pointing this way, and there's one for the other direction v pointing that way, and there's one for this guy, and so you get, some set like this, where I have an intersection of a slab, one for every unit direction. Okay? And the cool thing about this median is that it basically does this, which is kind of sweet. So here's a fact. Actually, it's a theorem. It's pretty serious. This is again by Lugosi and Mendelssohn. This is why they made this definition, because they wanted to prove this theorem. If x1, xn are IID copies of some random vector x with covariance at most identity, then with probability 1 minus 2 to the minus n, the mean of x is, you need this, order 1 plus something decaying with n, square root of d over n, 0.01 central. So they almost got our goal up to this error, which it turns out you sort of information theoretically need to pay. Okay? So that's cool. That says that we're almost there. That says that there exists, with very high probability, one of these medians, one of these central points. That wasn't even obvious to start with. And the second thing, this is a deterministic fact. This has nothing to do with samples from a probability distribution. The second thing is that if x and x prime are r 0.01 central, then x and x prime are close. Okay. So what this theorem says is that if I want to accomplish this goal, up to a little bit of error in this quantitative bound, all I have to do is find some rp central point for r as small as I can. Right? Yeah.
So the standard thing like center points, where you just have 3 samples come from 3 disjoint sets, those I guess don't satisfy the covariance property. Is that what happens?
I guess it will depend on how far apart the sets are.
Or one apart, say one.
I mean, they should.
So
then you should have
So what's
covariance
the
order
answer in
1.
that case?
You should end up with the middle, I think. Like, I'm not exactly sure the situation
So
you're
in the
asking
middle,
about.
when you draw the line, then, so now it's not going to be balanced. You have two-thirds of the points on one side and 1/3 on the other.
I see.
Just
Yeah, but remember, I mean, what will be the distances there? The distances will be order 1, right? And I only want to get within order 1. So I think maybe the high-level point here is that the median has constant bias from the mean in general.
Okay.
Is that, maybe that's sort of captured, like, in the one-dimensional case, right, you can't hope, at very best, if you output the median of x1 to xn, you're going to get close to like the population median. And the median, the population median of x, like without sampling, you know, it could be a constant distance away to the population mean. So you can't hope to do better than this order 1. And I think that's what's showing up in this case.
0, 1 random variable, and then you want the median, right? I guess everything's a median, right?
Yeah, everything's a median, but I don't distinguish between them because I'm okay with being distance order of 1. So in the case of a 0, 1 valued random variable, this is not so relevant because there I would prefer to use something that exploits the fact that my variable is bounded, right? The whole point of using a median was that I wanted to tolerate very nasty tail events. But a 0, 1 random variable doesn't really have such nasty tail events. Make sense? Okay. So, this solves the problem from an information theoretic standpoint. But now it's not clear how you would compute it, right? My eventual goal is to design algorithms, efficient algorithms which can compute high-dimensional medians. And, you know, like the naive thing for computing one of these RP central points really seems like it should require time that's exponential in dimension. Like, yeah.
Sorry, I'm missing something. I don't see how even from an information theory perspective, we've made progress. Like, couldn't we have just output E of x before, technically? Or sorry.
Oh, so
We haven't shown that it's possible to get, we haven't shown that there exists a point that is central like this.
no, we did. The expectation of x is central.
Well, sorry.
Well, I didn't show it, but
We could have output that before.
I didn't. So let's imagine in the back of our minds we wanted to solve some estimation problem where I'm getting samples from an unknown random vector.
Right.
So I didn't know the mean before.
I guess what I'm saying is, I don't see how with these samples,
Yeah.
we can compute an RP central point, even information theoretically, no more than we could have computed EX before.
Oh, let's discretize RD. So now all I have to be able to do is decide if a fixed point, if a particular point is RP central, right? Because I'm now going to just do brute force search. Now to decide if a fixed point is RP central, I have to check something for every unit direction. Let's discretize all the unit directions. So some horrible brute force search algorithm I'm claiming will find an RP central point. I'm not proving it. You have to make sure all the discretizations work, but I claim it will. Other questions? Okay, so let's do algorithms. Not at all clear how you would compute an RP central point, but here is a theorem that I don't think anyone has ever really properly written down a proof, but it's basically implicit in these two papers. So this is the case, by the way, for any list of points x1 up to xn. They don't need to be independent samples from a probability distribution or anything like that. If there exists an RP central point, let's be conservative here. Let's say, like, for all p bigger than 0, but then p needs to be independent of n in dimension. Let's say, think of p as a little constant. If there is an RP central point, then you can find an O of R, O of P central point in time polynomial in N and D. Okay? So this says that up to some constant factor losses, you can find an RP central point. And then outputting that point we'll again basically resolve this problem. Okay. So let me give you questions about the statement of this. Yeah.
If P is a constant, what does O of P?
Yeah, good. So let's put 100p here. I'm pretty sure that's true. Okay. Yeah.
So then we can find this in a certain amount of time. So this is with our sample sort of strategy, like
yeah. So now
samples from our distribution,
right.
Black box generating samples.
Right. So there's two things going on here. One is some kind of worst case problem, like I just give you a list of points, you find me a median.
Yeah.
Right. And now you're saying, okay, suppose I want to solve some kind of heavy-tailed statistical estimation task, like maybe I want to be close to the true mean with extremely high probability. I'll take samples. I'll run my black box algorithm to get a RP central point, and I'll output it.
I see. So this is purely about just getting a list of points in RD and finding
Yeah.
some sample points.
Yep.
Actually, even your definition of RP central point is defined only for samples, right? Only for points right now. You didn't define it for
Yeah, right. RP central points is defined. Yeah, it doesn't even have to really be samples, right? Just a list of vectors in RD. That's always the input to these problems. Good. Okay. So what's the algorithm look like? Let me show you the idea. So this is an algorithm mostly drawn from this paper. There was an algorithm like it in this paper, but it was a lot more complicated. So let me tell you about this algorithm due to these other guys. The idea is that we're going to try to form a series of iterates. So we're going to start at some guess of a starting point. So here's my data. Here's my points, x1, x2, x3, and so forth. And I know that there exists an RP central point, right? In fact, maybe put it in a different color. I know that there exists a central point x. Okay? I'm going to start at some guess of a central point, y. And I'm going to try to get close to x. Right? I'm going to try to find some direction in which to move y to get closer to some RP central point. The key observation is that if y is far enough away from x, then, well, suppose I look at what's going on in the direction from x to y. In the direction from x to y, I know that x is central, so most of the points are close to x in this direction. But if y is far from x, then that means most of the points are far from y in this direction. Okay? So one characterization of the direction from y to x, the direction where I would like to move, is that it's a direction where many points are far from y. Right? It's sort of a witness to the fact that y is not central. Right? And what you can actually show is that any direction like that, any direction where there are a lot of points far away from y, is a good direction to update y to get closer to a central point x. Okay? So I will actually prove that to you in a minute. But that tells us that what we need to do is we need to find some direction. I know y. Y is my current guess. I know these points x1 up to xn, and I want to find some direction where there are a lot of points far away from y in that direction. And we're going to do this with a semi-definite program. Okay? So maybe this is my descent direction v. And how to find v? Finding a direction with a lot of, yeah.
Are you restricting yourself to output one of the points?
No. I can output any point in RD that I want. And in fact, if I had to output one of the points, I think it wouldn't be possible. Like you wouldn't be able. It's not true that one of the x's satisfies this. So suppose I want to find a direction like this. I'm going to use a semi-definite program. When you set up a semi-definite program, you often start by setting up a quadratic program. So let me set up a quadratic program. I'm going to have a quadratic program where the variables, I have some indicator variables, b1 up to bn. They're in 0, 1, and they just say, is point xi an outlier? Is it far in this direction v? I have some variables to represent a direction. So this is like a vector in RD. Its norm is 1. And my goal is to maximize the number of faraway points. Well, and now I need to say, what does it mean to be a faraway point? Here's the quadratic constraint. Let's say 10 RBI. So what's going on here? If I set BI to 0, I get 0 greater than 0, and this constraint is trivially satisfied. But my goal is to set as many BIs to 1 as I possibly can, right? If I set BI to 1, then this constraint says that if I project in the direction v, xi is far from y, at least distance 10 times r. Okay? So this is a quadratic program. You can relax it to a semi-definite program. Let me see how I'm doing on time. We go to like quarter till, 10 till? What do we do, Anish? All the way. Oh, until like tomorrow. We'll go all night. All right. Do the whole proof. OK. So you can relax this to an SDP. And I think, unless you guys really want, I'm not going to do it, because it's pretty standard how you would get an SDP relaxation of this. I'm just going to write SDP relaxation, and you can have it in your imaginations. Use a standard semi-definite programming relaxation of this problem. And the key thing we need to show is that if I solve the SDP relaxation of this thing, and the SDP tells me, hey, here's a feasible solution that says, with like large objective value, what does that mean? It means there look like there are a lot of outliers. There look like there's a lot of points far away from y in this direction. I need to be able to actually find such a direction, right? I need to solve a rounding problem. So the key fact is this, key lemma. If you're given some SDP solution with value, let's say 0.9n. So that's like a solution that says, I think there's a direction in which 90% of the points are far away from y. Then you can round to get a unit vector v such that xi minus y inner product v is greater than 2 times r for 0.1n of the xi's. OK. So the rounding scheme is completely standard. You do some kind of Gaussian sampling if that's something familiar to you. Nothing, and the analysis is totally straightforward. Nothing fancy is happening here. But let's just see what happens. So we said, the SDP said, I have a vector, I have a direction where there 90% of the guys are at distance 10 times r away. And I'll find you a direction where 10% of the guys are at distance 2 times r away. So I lost some quantitative constants, but I still found a direction in which a lot of the x's were far away. OK? And now all you have to do is show that moving in that direction is a good idea. I just want to make sure I didn't lie to you. I mean, I'm definitely lying to you, but in an objectionable way. Yeah, cool. So now all you need to do is show that moving in that direction is a good idea. So that proof is super simple. Now I know that, like, let's say x was p central for p being 0.01, right? 99% of the points are close to x in this direction. And 10% of the points are far from y. So there exists some point, like maybe it's this one, which is close to x and far from y. Yeah? Let's call it xi. And now all I'm going to do is I'm going to measure my my distance to x in terms of this point. So what I'm going to do is I'm going to say, well, I want to show that moving in the direction v improves my life. And what I have to do for that is show that y minus x, I think it should be x minus y, actually. That x minus y and v, I need to show that these are correlated. right? Then I can run some kind of standard gradient descent analysis, and I can show that moving in the v direction gets y closer to x. So for this, all I'm going to do is I'm going to write this as xi minus y v plus, minus xi minus x v. Okay, I just added and subtracted the point xi. And now I knew that y was far from xi, and x was close to xi. So this guy is at least twice r, and this guy is at most r. So this is at least 2r minus r is at least r. Okay, so now you have to do a little bit of parameter tracking to make sure that this is enough correlation that you'll converge in polynomial time. You have to set r correctly and so forth, but none of that is super difficult. And this is basically the algorithm. Okay, is you're going to pick some starting point. Your starting point could be the geometric median or the coordinate-wise median, just something kind of naive, and then you're going to update it to make progress closer to x, at each step solving a semi-definite program to find a direction to go. Okay? Done. Questions? Yeah.
What if y is kind of close to x, but not close enough to x?
Good question. So what does close enough mean? It turns out that you can show that this whole thing will work as long as y is, let's say, distance, let's say 100r or something like that, because basically that will mean that there's a feasible solution to this SDP. So then I'll get a good solution, so I'll be able to round. If it is closer than distance 100r to x, then what I want to note is that because x is r p central, y is 100r p central. Okay? Because I can measure the distance of y to any point by first going to x and then going to that point. So that's a good question. This is where I'm going to lose a constant factor in the degree of centrality that I get.
So we didn't lose anything in our p centrality?
I lost a little bit in the p centrality because I needed to do this kind of pigeonhole argument here. Right, so there's kind of two ways the algorithm could get stuck, I guess. You could get stuck, yeah, that's not a good explanation. Yeah, instead of trying to figure this out live, let me say that I believe the loss in p comes from the fact that I needed to have some kind of pigeonhole business going here, where there's a point that's far from y and close to x, and the loss in r should come from what happens at the end of the algorithm. And if we want to go through it.
The key lemma also seems to lose in p, no?
What's that?
The key lemma you have seems to lose p right away, no? You were assuming that there was an SDP solution where 0.9 and things were...
Yeah. This loses in p, but the question is whether this loss in p translates to this loss in p. And I sort of thought it obviously did, and now I'm standing in front of a board and I don't quite know why it's obvious, but maybe we'll try to figure it out afterwards. Yeah?
A question about the algorithm.
Yeah.
How far in the direction will you move?
I mean, you move, you do the usual gradient descent thing where you move sort of like a small constant times the correlation that you got. If you just want a polynomial time algorithm, then you don't really care. 1 over poly dimension will be good enough. Yeah.
So do you have to know R and P for this algorithm to work, or do you just guess them?
Good. I think that you can definitely be adaptive to them if you lose some logarithmic factors. Sorry. Oh, do you have to know R for this worst case algorithm to work? I think you should be able to guess them. And somebody always asks me this, and I don't have a good answer, and I should really figure it out. I think the right answer is you can guess them, but actually I'm not 100% sure.
But there are only two...
They're just two numbers, so
Can you not
Just
guess in half.
The hard
Yeah.
part would be, can you tell if you've gone too small and your gradient descent has failed? That's the thing that I'm not clear about.
Can you tell if you've gone too small and your gradient descent has failed?
Presumably, if you pick too small an R and P, this will fail because your gradient descent will not converge to the right point.
I mean, if you pick too small in R and P, your SDP is gonna tell you, because because your SDP will become infeasible. Yeah.
Actually,
Yeah.
I'm still confused. So if your SDP, sorry, if you your key lemma implies, I think, that if at a certain point SDP becomes infeasible, then
You're
that
RP
is a
central.
point,
Then you're central.
your 2R, 0.1 or sorry 0.9 central.
Yes.
That's where you lost P.
But then you can do this trick where you say, if you're 2R 0.9 central, then you're close in L2 to X by this pigeonhole thing, and X was R 0.1 central. So now I can upgrade the 0.9 to a 0.1. Yeah? A little funny. Seems fishy.
I didn't follow all of it, but, so you're doing some algorithm, you're repeating it. And so the reason it converges or terminates is because?
Oh, you need to show that you're starting, so right, so I said you need to do a little bit of kind of routine stuff. You need to show that you make, say, 1 over poly dimension progress in every step, and you need to show that you can start it at some point that is like.
Progress is what, your step size?
Progress is like your L2 distance, progress is like your L2 distance to the RP central point that you know exists.
I see. Okay, so
Okay.
the step size is going to decrease or something.
Yeah, step size will decrease as you get closer. I mean, like, in the iteration part of the algorithm, this outer, iteration to get closer to X, there's nothing fancy going on. It's a 100% standard gradient descent analysis. The only point is that I can find some direction that's correlated with the direction from X to Y. This is where something non-trivial is happening, where I have to use an SDP to find such a direction. Yeah?
Is there a way to think of the descent direction as like gradient of some objective function?
Yeah, norm of X minus Y squared.
But then you don't know the x though.
Yeah, the point is that I can find a gradient of that function without knowing X. Okay. Cool. So now I want to tell you about some stuff that we did more recently, where we said, okay, this whole goal, like everything we did here, was basically because we wanted some way to get close to the mean of a random vector with extremely high probability. And I said, if you can do this, then you can put this together with some other tricks. The big trick is called median of means, which you might have heard of. You can put this together with some other tricks, and you can get really cool theorems about how to estimate the mean of a random vector, even when you make very mild assumptions on it. But now, you might want to be close to something like the mean of a random vector in some different norm. Okay, this was all about getting close in L2. But what if you want to get close in some other norm? So it turns out that from the non-algorithmic standpoint, you can basically generalize all these definitions in a super clean way, and you can prove analogs of this theorem, an analog of this theorem for basically any norm. This is again due to Lugosi and Mendelssohn. So that's cool. But when you want to deal with other norms algorithmically, life becomes much harder. So for the next part of the talk, I want to talk about this paper where we focused on the special case of spectral norm. Okay, and why would you focus on spectral norm? Well, the killer application of getting close to something in spectral norm is doing covariance estimation of a heavy-tailed random variable. Okay? So let's say what the setting is, and for that I need to see what the setting is. Cool. Yeah. Let's not erase that because I want to compare. Okay, so medians for spectral norm. So my goal is now, I wanted to give an analogous goal here. And notice that my goal here, because I had this hidden idea that what I wanted to do was estimate the mean of a random vector, I talked about taking the median of a bunch of samples from that random vector. Because my hidden goal here is to find the covariance of a random vector, I'm going to tell you some slightly funny distribution of random matrices that whose median I want to compute. And I'm not going to tell you exactly why this is the right distribution, but it follows from this median of means idea if you've seen it. But otherwise, you just have to take me on faith. So imagine that you have some random vector x on Rd. And it has, let's say, bounded, I'm not going to say exactly what bounded means, bounded constant order moments. Like maybe its 8th moments are bounded, for example. I don't know, some constant, right? Point being, it could still, its 9th moments might be infinite. It could still be pretty nasty. And let's just say that it has covariance. Now I'm not going to talk about covariance identity because my whole goal was to estimate a covariance, so I better kind of deal with an unknown covariance. It's a matrix sigma. But just for normalization purposes, so that I don't have to write a whole bunch of matrix norms of sigma all over the place, I'm going to assume that the trace of sigma is roughly the dimension d, and the spectral norm of sigma, it's like 1. So this is sort of comparable to the identity matrix in a loose sense. And now the relevant distribution of matrices that's going to play the role of these vectors here is a little bit funny. What you do is you take, you define a random matrix, which is the average of the tensor, the outer product of m independent samples from x. Okay? Think of m as being like a big constant. This is actually going to be interesting for a wide range of m's, but for concreteness, let's think of m as a big constant. Okay, so I draw 1,000 samples, and I take their outer products, and I sum them up. I take the empirical covariance of that 1,000 samples. That's my random vector z, or random matrix z. And now my goal is some median of n copies of z, such that the spectral norm distance between that median and sigma is order 1 with probability 1 minus 2 to the minus. Now I actually need to depend. Oh, sorry. I'm completely lying. Well, let's lie and then unlie. 2 to the minus n. Okay, nice goal. No, it's not a nice goal. Sorry. I was just trying to copy that, and I got really confused. This is trivial. Does anybody see why? Just output the zero matrix or something, right? The point I'm making here is that this setting is a little bit harder to get right, and sometimes even when you're giving a talk, you get it wrong. So I sort of said that for normalization, I want this thing to have maximum eigenvalue 1. And that means that if I just output the zero matrix, I'm going to get within spectral distance 1. So OK, let's get within distance epsilon for some tiny number epsilon. And let's just get something that's at least if epsilon's a small constant, I'll get something like 2 to the minus n. OK? So I admit it's not totally obvious why you want to solve this goal. I'm claiming you have to trust me that if you can do this, you can get a really cool covariance estimation algorithm, which basically estimates the covariance as well as if x were Gaussian, but assuming much weaker conditions.
So what norm would you have the convergence in for that estimator?
Spectral norm. This is spectral norm.
I see. So in particular, but it doesn't mean that, for example, I would get all eigenvalues correct in a multiplicative 1 plus epsilon, for example.
I don't think so.
Okay.
Actually, I don't know how to define an estimator that does that. That's a tricky problem.
But that's what you would be able to do if x was a Gaussian, right?
You're right. So if I measure by this criterion, by the spectral norm criterion, then I'm doing as well. If I want some kind of PSD order sense, I think it does not do as well. Because it's not an affinely invariant estimator. Okay, good question. So now that we have a goal, we could try to carry out our whole program from before, right? We can try to make a definition. And actually, we don't have to do it. So Lugosi and Mendelssohn, who made that definition, they did it for us for this one too. And you don't have to do anything all that different, actually, to define a median which will satisfy this property. So I'll define it for you. But the whole difficulty is going to be algorithmic, not in the definitions. So you define a matrix now. D by D is RP central if for all unit vectors v, I take my zi's. This is RP central with respect to a list of matrices z1 up to zn. Now I look in the direction VV transpose. Okay? This is like the quadratic form of this difference. If this is bigger than R, for at most Pn zi's. Okay? So the only difference from before was what was the meaning of a unit direction. In this case, the norm was L2, and the meaning of a unit direction is a unit L2 direction.
M is symmetric, or?
Yeah, let's assume M is symmetric. I mean, I'm taking quadratic. No, it doesn't have to be positive definite.
Positive semi-definite.
No. I mean, just any matrix. Like, I can make this definition for any matrix I want, right? It's, you could assume it's symmetric because I'm always measuring its quadratic form, not its bilinear form. So it doesn't matter that much. Right, what is the meaning of a unit direction here? Well, I care about spectral norm. So a unit direction should be a member of the unit ball of the dual of the spectral norm, which is the nuclear norm ball, which is like this guy. Okay? So let's put absolute values. Cool. So it turns out that you can prove an analogous theorem to the non-algorithmic theorem of Lugosi and Mendelssohn for this notion of median in this setting. Okay, so there's a theorem. Now it's due to Mendelssohn and Zhivatovsky. And it says that in this setting, with probability 1 minus 2 to the minus omega epsilon n, the true covariance sigma is epsilon. Again, you pay this root d over n factor, central. And also, you get the same thing as we did before. If m and m prime are both central, then m minus m prime is small. This is, again, spectral norm for, this is, say, 0.1. Okay? So we get the same theorem as we did before. It says that the true covariance is central. And if I find two central points, then they're close to each other. So if I just want to do the non-algorithmic version of things, I just brute force search for a central point.
So,
Yeah.
Can I ask a question?
Yeah.
So I'm a bit confused with the scales. How large is R supposed to be in the setting that you defined?
R should be, I mean, think of it as like a tiny, okay, a good setting to think of is that n is like bigger than d. I saw a sample for every direction.
Small m is bigger than d?
No, little n is bigger than d. Okay, so I saw a sample for any direction, and then it's like a small constant.
But then it's a bit confusing. So it's like zi's are an average of just a constantly many samples, right?
Yeah.
So even for like a Gaussian random vector, zi minus m would have spectral norm root d or d or something, the dimension, right? Because it's like a
z. I mean,
constantly many samples.
right. A single zi is not good, but I give you n zi's. I give you n of them. So I gave you like a large constant times n total number of samples.
Okay, but I guess I'm confused because your definition I'm saying will not be satisfied, no? It's like no matrix will satisfy that definition.
No, it will. This does not say that you're close in spectral norm. That does not say any particular zi is close in spectral norm. What it says is that for every fixed direction, 90% of the z's get the quadratic form right. This is kind of surprising, right? It's even surprising for Gaussians, right? This says that you, like, if you take a bunch of matrices that are like 10 samples from a Gaussian, sum of xi transpose, for any fixed direction, 90% of those are getting the quadratic form right. It's just that each one of them actually also has a very large kernel, so of course it's not close in spectral norm. Make sense?
Yeah.
Okay. So I'm going to wrap up by telling you a result. And I should say that the algorithms in this case, like, they're much messier than in the case of L2 estimation. For starters, I actually have no idea how to give a worst case algorithm that computes a central point, like we did in the case of L2. Right? For L2, I got to just ignore the fact that my things came from, were samples from some distribution, and I just showed you how to compute a central point. Here I have no idea how to do that. It would be really cool if you can do it. So we resorted to like an average case analysis, an average case kind of approach, where we said, all right, what distributions of points do we want to handle? Well, because we want to do covariance estimation, we really want to handle these points, right? We want to handle like independent samples from this kind of matrix. And what we show is that, now I'm going to write theorem in quotations because I'm really getting informal towards the end of the talk here. But what we show is that in this setting, if you have to make an additional assumption on the random vector x, which is that it's what's called certifiably hypercontractive, which shows up a lot these days in the algorithms for high-dimensional statistics literature. Under some additional assumption on the 8th moments of x, still the 9th moments might not exist, you can find a epsilon plus root d over n to the 1/4, 0.01 central point. And actually, there should really be some logarithmic factors sitting in front of here. So there's some polylogarithmic factors that are being dropped. Okay, so this there's some quantitative gap. So we lost a couple things from the L2 case. One was we had to do some average case analysis. And this happens with probability 1 minus 2 to the minus omega epsilon n. So we kept a few things and we lost a few things. We kept that we can find some central point and we can do it with extremely high probability, which was the goal of our median. So that's good. We lost that we got the right degree of centrality. In the case of L2, we really got the right answer, and here we're off by some quantitative polynomial amount. And you might ask whether that was inherent. So I'm going to address that towards the very end. Let me show you very briefly what the algorithm looks like, because I have like 3 minutes. Cool. The algorithm here is really the same. You're going to start at some point. You're going to try to descend towards a central point, like sigma. And to do it, I have to find some direction in which to move. Now a direction is like a VV transpose. So now what am I doing at every step? I'm looking for some direction, some vector v, such that like the quadratic form of v at my current guess is too large by comparison to the quadratic form of the z's. And I'm just going to show you that you can set up the analog to the quadratic program we saw before. So here's the analog to the quadratic program for finding a descent direction. Again, I'm going to try to maximize the number of outlier-looking zi's, such that, okay, b1 up to bn are in 0, 1. V is a unit direction. And now I write this constraint, which is not quadratic. bi times zi minus my current guess m at VV transpose is bigger than, say, 10 times r times bi. Okay? So this is a degree 3 polynomial optimization problem. And what we do is we use this sum of squares semi-definite programming method, which gives you canonical SDP relaxations for higher degree polynomial optimization problems. And our key technical contribution is basically an average case analysis of this semi-definite program, which is able to show that with extremely high probability, it recovers a good descent direction. Okay, so this analysis for people who have seen these before, it has kind of the flavor of like the analysis you do for refutation of random CSPs, except that we need some extra tricks to upgrade the probability that this thing succeeds to extremely high probability, even in the setting that we're working with these nasty, heavy-tailed random vectors. Okay, so that's the technical business that goes on. You analyze this SDP, you use it to find your descent directions, and you can prove this theorem. And the very last thing I want to say is, well, this theorem isn't that satisfying, right? Like, it didn't do the optimal thing, whereas we managed to do it in the L2 case. And you might ask, could we have done better? I don't know the answer, and I would love to have strong evidence that you can't do better. But we have some mild evidence. So I will tell you what the mild evidence is, and then I'll be done. So what is the mild evidence that you can't do better? What we can do is we can construct a distribution of random vectors such that it seems like it should be hard to distinguish you can just construct a pair of distributions that seem like they should be hard to distinguish, where under one of the distributions there is an outlier, like a good descent direction for some parameter here less than this number, and for one of the distributions there is not a good descent direction. Okay, so a little bit more formally, what we can do is we can construct a joint distribution on a whole list of samples, x1 to like x100n, such that if you group these things up, you look at these z matrices, zn, under one distribution, with high probability there exists some vector v such that like zi minus identity VV transpose is greater than root d over something a little bit smaller than end of the 1/4, 0.26, let's say. And the other distribution is just like Gaussians everywhere, and it turns out you can show that this doesn't happen for Gaussians. And furthermore, 1 and 2 have approximately matching moments to degree like almost polynomial in the dimension of this thing. Okay, so the intuition here, okay, you have to believe me that there's some reasonable notion of approximate moment matching, and I'm happy to discuss it later. But the idea here is that there's some distribution of these random matrices where if your current guess was identity, you would have a hard time distinguishing whether you should make a new update or whether you're done. So this is some very mild evidence that maybe it's hard to get past n to the 1/4 in the case of covariance estimation, whereas we were able to do something optimal for mean estimation. Okay, so that's it. Thank you for all of your attention. I'll be around for a couple days.